Okay, in this video, I'm going to review the connection between definite integrals and sigma notation and how we write Riemann sums using sigma notation. So on the screen in front of you, you have a sample definite integral. Remember, a and b are the bounds. That's how far the interval goes from a to b. And then this is finding the area under the curve of f of x. Okay. Before we did integrals, we talked about these things called Riemann sums as a way of estimating the area under a curve. And what we found is if we did 6 rectangles, we had a pretty good estimate. And then if we doubled that, we had a better estimate. And then if we could actually find all the rectangles, all n of them as n goes to infinity, then what we would have is the exact area under the curve. So this is the sigma notation setup. We start out by writing the limit as n goes to infinity, and then j, that's going to count the rectangles as we move across, and we want to go from the first one to the nth one, right? And then f of a plus j delta x represents the height of the rectangle. The delta x is how far across the width of the rectangle. And so when you multiply these together for each individual rectangle, the sigma says to add them up. Okay? Important to notice that this a here does match the lower bound of the integral, and that delta x is defined by b minus a over 2. All right, here we go. Here's an example. Always makes more sense when we have examples. So your directions are to rewrite this definite integral using sigma notation. So how many rectangles do we want? We want all of them. So we're always going to start out with the limit as n goes to infinity. And you can use j or k or I, it doesn't matter, but your indices need to go from 1 to n. Okay, and so we're going to do f of a, and this is a. So f of 1 plus, and then this is important, the function. So going back to this, I want to do f of a plus j delta x. So we're going to keep the j there, and then in place of the delta x, we're going to put delta x here is 3 minus 1 over n. So it's 2 over n, right? So f of a plus j delta x times delta x, right? So now all we need to do is put this into the function f that we're given, right? So rewriting this over again, j equals 1 to n, the limit as n goes to infinity. So we're going to have 2, and then here's 1 plus 2j over n. That's putting this in for x, right? Plus 1. And then that whole thing is multiplied by delta x. Okay? So if you can see here, this used to be x, and we've replaced x with in the function 2x plus 1. All right, and then you don't have to do anything to it. You're done. That's fine. Now going back the other direction is a little bit trickier. So I'm going to do a pretty simple one. What if I give you the limit as n goes to infinity? And then sigma notation tells you that I'm going to go from 1 to n, just like before. And we're going to have k over n cubed times 1 over n. So really what we're doing is we're matching it to that standard notation for it. This is going to represent delta x. And so what that means is that b minus a over n has to be 1 over n. So the bounds on the integral have to be 1 apart. All right. And then this k over n cubed is simply delta x, k times delta x cubed. And so the function we can see here is x cubed. And because there is not any plus a value in here, we are assuming, or no, we are not assuming, we're actually seeing that the a value is going to be, oh, how did that happen? Wow. 0 to 1. of x cubed dx. All right, so let me go ahead and put that back up there. So it was k over n cubed times 1 over n. So this is a little trickier because you're doing a little bit of guesswork, but when you're done, it's always a good idea to do the procedure we did up there and make sure that you end up with what you started with. Okay, I hope that was helpful.